it's exceptionally easy to apply rotational cryptanalysis to ARX that do not have constants. The reason for this is there exists a very basic formula which allows to compute the rotational probability of ARX. Well, in this work, we show that this very basic formula is actually incorrect. So the formula by which we have computed the probability of ARX primitive is incorrect. Basically, with this work, we show why it's incorrect, what's incorrect with the formula, and how to fix it. So let's start from the beginning. First, let's recall what's rotational cryptanalysis. So rotational cryptanalysis operates with something that's called rotational pair. Basically, you have two states. We are trying to analyze, to launch rotational cryptanalysis of some block cipher or hash function or compression function which has, let's say, one input. So rotational cryptanalysis operates on something that's called rotational pair of inputs. Basically, you take one state with all random inputs, and in the second state, you rotate all words of the first state to a certain fixed amount R. So rotational cryptanalysis asks the question, can a rotational pair of input produce a rotational pair of output? So if I start with a rotational pair of inputs, can at the output, I also get this rotational property. And rotational probability is the probability that the chance that this will happen. Okay, it's quite simple and trivial. So rotational cryptanalysis is mostly applied to ARX primitive, ciphers and hash functions that have only three operations: additions, XOR, and rotations. So if we investigate independently the rotational probability of these operations, we'll find out that the rotational probability of rotation is 1. From here we can easily see why. The rotational probability of XOR is also 1. And only the rotational probability of modular addition is less than 1. It's at least 1/4, and it depends on the rotation amount R and on the size of the words N. So we assume that these ARX primitives do not have constants because the constants can completely destroy the rotational property. Okay? So we're working only with ARX with no constants. So because only the additions have a rotational probability of 1, we can easily compute the rotational probability of ARX by this basic formula which says that, okay, if the rotational probability of one modular addition is P plus, and ARX has Q modular additions, then the rotational probability of the whole primitive is P to Q. I mean, it's quite simple, right? I multiply Q times the rotational probability of one addition. Because of this simple formula, as I said before, it's exceptionally easy to apply rotational cryptanalysis to ARX. Basically, if this rotational probability is more than 2 to the minus size of the state of the ARX primitive, then I can claim I have rotational distinguishers, right? And then the primitive has weakness, and then we can explore more if we can recover keys and so on. However, in several results, it was reported that maybe this basic formula is incorrect. So I just want to clarify, I'm the author of these results. So one of the results is the AsiaQuid paper with Dmitry and Christian, which was later published in Journal of Cryptology, where we tried to apply rotational cryptanalysis to Skein. And there we say the rotational probability of one round of Skein is this much, but the probability of 2 rounds found experimentally is this much, instead of this. So if for 1 round is P, then for 2 rounds it should be P squared. But as you can see, it's not P squared, it's not this number square, but actually it's a little bit lower. And then there is another paper, analysis of Blake 2, published at CTRSA 2014, where we say that in Blake 2 you have this G function, where we say for the whole G function we obtain that the rotational probability is this much, but the experiment showed that the actual probability is slightly lower. Okay, so instead of 2 to the minus 8.4, we get something slightly lower. So maybe there is no, from these claims you can see the discrepancy is not too big, but why do we get difference at all? How come the rotational probability does not follow this simple and nice formula? So basically why it doesn't fall is the topic of research of this result. and we're gonna see why not. Okay, so let's try to understand why and how to fix. So first you have to understand the rotational analysis is a statistical attack, and probability of such attacks is computed under the assumption that at each non-linear operations the inputs are completely random. Okay, whenever we deal with statistical attacks, differential, linear, and so on, we almost always assume that at the inputs of each non-linear operations, the inputs are completely random, right? And then we can nicely find the probability of these statistical attacks. This is assumed to be true because we think that the subkeys provide enough randomness, because the other transformation in the primitive provide enough entropy, and so on. Well, the case of differential analysis has been investigated by Ley and Massey, and actually they focus on the way how the probability was computed in differential analysis by Biham and Shamir. And they said that, Biham and Shamir had all the right to compute the probability of the differential characteristic there as a product of probabilities of all one-round characteristics under certain assumptions. So their main point is the introduction of so-called Markov ciphers. So let's take a look what Markov cipher is. So it says Markov cipher is an iterated cipher with round function f, which takes as an input the state and the round key, such that for all differences, input difference alpha and output difference beta, the probability of the one round characteristic, difference alpha goes to difference beta, does not depend on the input state when the subkey, when the round key is random. I think there is a small misconception about what Markov cipher is. I think some of the people think that Markov cipher we assume all the keys are random and independent. But actually this is not the case. We have to understand once for all that in Markov cipher we assume that, okay, if I have one round differential characteristic with some input difference and output difference, then the probability of this characteristic will not depend on the input state as long as the round key is random. Okay? So for any input state, as long as the input difference is alpha, the output difference will be beta with this probability. So, and then Lema say that if the cipher is Markov and all round keys are independent, chosen at random, then actually you can multiply the probability of you can produce the probability of the whole characteristic on R rounds as a product of probabilities of all these one round characteristics. In other words, only then you can multiply the probability of this of all nonlinear operations. However, if the cipher is not Markov and the round keys are not independent, by the way, this is a necessary condition, it's not sufficient. So if the cipher is not Markov or the round keys are independent, Ley must say, we don't know, you have to investigate more. Make sure you investigate more. So in practice, we always assume that the cipher is Markov and the round keys are independent. Why? Because the key schedule we assume provides sufficiently good random keys. They're never independent, but we assume they're random. And we also assume always that the cipher is Markov, even without checking if this one round differential characteristic has this type of probability. So the same assumption we use not only in differential analysis, we also use in other statistical attacks. But let's give immediately a counterexample of this thing with respect to rotational cryptanalysis. Here on this figure I have two ARX primitives. Both have two modular additions, so by the basic formula I should obtain the same rotational probability for both of them. So the only difference, they even have the same number of operations, the only difference is here the rotation on the left branch, here it's on the left, here on the right. So if I start with two random inputs, the probability here that the output is rotational is the same as here, right? But the thing is, in rotational cryptanalysis, the rotational probability highly depends on the most significant bit. So in this case, I'm going to get rotational output pair, but this most significant bit will be biased towards 1. Same thing here. And then when I hit the next modular addition, because I have bias on 1, and the previous formula assumes that I don't have any bias, the rotational probability here will be slightly lower than what the formula predicts. In this case, because of the rotation, the most significant bit was biased towards 1, but the rotation shifts this bit to another position, and some unbiased bit come to most significant place, and here the formula, the basic formula, will predict correct rotational probability. So in this case, as you can see, basically this just shows that the basic formula is incorrect. We have to take into account some other facts. Why is it incorrect? Because this is definitely not a Markov cipher. I don't even have subkeys XORed everywhere. So let's try to realize the problem. So in this case, I obtained all nicely because I had rotations. So because kind of the rotations randomize, so even here I had some biased bits, the most significant bits was biased, but the rotations successfully randomized this thing. So if I have rotation, I can assume that their output is probably random, and then I can use my basic formula. The same thing will have if I have XOR, will happen if I have XOR, because if I XOR a random word, of course the output will be random. However, if I have consecutive modular additions, then the basic formula will definitely not work. So I have to focus in particular on the case of this chain modular addition. So we call this sequence of modular addition, chains modular additions. So again, if I have ARX primitive, I have to take into account these chain modular additions. They cannot be computed by the basic formula, but they can be computed by the formula given here. So if I have some k random n-bit words, the probability that after each modular addition, the rotational property will be preserved is this much. Okay? So in this case, I have k minus 1 modular additions. I have to compute according to this probability, not according to the basic formula. So we use this GNU library to plug in this formula and plug different numbers here, and we came up with something like this. So this is a comparison of the old and the new rotational probabilities when the rotation amount is 1. So by the old theorem, this is what the old formula predicts. Look, if I have 32 modular addition, the old formula predicts this very high rotational probability. By the new formula, the rotational probability is much, much less. There is a huge discrepancy in this thing. Of course, we run different experiments to confirm that actually this is how, small scales of course, of ARX primitives, and the experiments confirm that our new lemma predicts correct rotational probability. So let's see applications. Okay, so how we compute the rotational probability of ARX now by the new lemma. First, we have to find all maximal chains of modular additions, then compute the rotational probability of each chain independently, and only then we can multiply the probabilities of all chain to obtain the rotational probability of the whole ARX. So first, let's try to apply to Blake, which is a hash function already in use. It's based on the previous Blake, which was a final round candidate. So Blake is based on this 2024-bit permutation, and there is already a result that claims rotational attack on all 12 rounds. By the way, I'm one of the co-authors that claims this result. And the claimed rotational probability is this much. So this is Blake, the permutation of Blake. It's kind of complex. I have 16 words. So let's try to apply our new algorithm. So first thing, I have to detect the chains of modular addition. So this is my first chain. See, I have modular addition, and they're not interrupted by any XOR or rotation. This is my second chain. I don't know if you see it here. And then in total, I can detect 8 chains. In one round of Blake, I can detect 8 chains. So basically, I can concatenate more rounds. As you can see that the chains always start in even words and end in even words. So if I concatenate more chains, they just get, their length just extends, but they're still not interrupted by any rotation and XOR. So then, for example, if I have, let's say, 8 rounds of this, so all of these, each of these 8 chains will have 4 additions and 8 rounds, so basically 32 additions. So I find the rotational probability of these 32 modular additions according to the new lemma, and it's this much. And because I have 8 chains, I find the total rotational probability of Blake 2, of the permutation of Blake 2, it's this much. So actually, we cannot even attack 8 rounds, let alone 12 as claimed before. The best we can go is 7 rounds. Okay, now let's try to apply to Skyne. Again, another SHA-3 final round candidate. It's a 72-round ARX with rotational constants, but the constants were rotational in the first two versions. The third version changed. So we had some previous results where we claimed rotational analysis on 42 rounds of Skyne, but the analysis was quite complex because it was not trivial there, and we used something called rotational errors and rotational correction and so on. So now we are not going to analyze. So this is the 4-round of Skyne. Here we have the addition of subkeys. So we're going to investigate kind of simpler variant without any subkeys and counters. So let's try to apply the new analysis. So first we detect the chains. This is the first chain. See, it goes nothing but modular additions over 4 rounds. Then I have the second chain. Actually, I can find 4 chains. Again, you can extend, because again, they start with even words that end with even words. So if I extend on, let's say 28 rounds, they will never get interrupted. And I can compute the rotational probability according to the new lemma, find the total probability as a product. So basically, I can only attack 28 rounds of this simplified version of Skyne, but not more. So in the old paper, we claimed we can attack 42 rounds when the rotational amount is 2, but taking into account all the keys and all these rotational corrections and rotational errors. With the new analysis, we say, listen, even if you remove all the sub-keys and you take rotation amount R, which has higher rotational probability, we can attack only 28 rounds. Just to make it clear, we cannot disprove in this case the old result because of these rotational corrections and errors. However, it looks a bit suspicious. So to conclude, be very careful when you take this Markov cipher assumptions for granted and when you work with statistical attacks, because it may not be true. Be very careful when you're doing the same thing in regards to rotational cryptanalysis. And a few open problems: how to deal with these rotational corrections, how to deal with more complex additions. So basically, when you have 3 or 4 at the same time, we still don't have the formulas. They look kind of really complex. Maybe you can try to come up with something better. That's all. Thank you.
Thanks, Ivica. Do you have any questions for Ivica? Tome?
In one of the previous slides, you gave an example, the one where you show that 2 ciphers were not the same, or 2 variants of the same thing. Mm-hmm. Yeah, here. So if you XOR the K key, this would simplify everything, right?
Yes,
this would
correct.
break any chain.
Yeah, that's the thing I left out of the slides. We have this thing about the paper. Actually, it matters if you XOR the key and if you modularly add the key. It makes all the difference, because the XOR of the key will break the chain and the rotational probability will will increase. Good point, yes. Thank you.
Maybe another question? Oh, here you go.
So the probability is always smaller? No.
Yes.
Because I mean, you have the same effect, not only for rotational, but whenever you kind of, I guess with normal differences, you would have the
The
same.
way we compute what we assume, what we expect, so we want, we want this thing to happen. So if I modularly add, rotate, I get this. Maybe you're gonna get much higher probability if you don't want this to be 0, but plus some constant here, some number, some value, and then maybe because of this, you're gonna get much higher rotational probability. Do you know what I mean? Because here we want ideal. So this thing plus rotation to be the first rotation plus the second rotation. Now let's say if we want first rotation plus second rotation plus 1. In that case, because I add 1, maybe the rotational probability now will increase, whereas in the old case it was much lower because I have these chains.
maybe I have a question also.
Yes.
So, how strong is the evidence in your opinion that this is the last word, at least on this simplified way of looking at primitives? I mean, the reason why I'm asking is that it's hard to experimentally verify. The probabilities don't really scale well with word sizes, so it's hard to verify longer addition change or many rounds.
We experimented with many round reduce, and kind of the new formulas confirm that everything is right now. I mean, you never know. Maybe it will depend on the key schedule. Of course, we took some random inputs and all the stuff, but now it looks fine.
Okay, any more questions? Otherwise, join me in thanking Ivica again.